This is chapter 11, Reactions of Alcohols, which I have divided into 3 different parts. For my students at Baylor University, this is a chapter that you're going to listen all by yourself, and then when you come back from Thanksgiving, we're going to just work problems and do a lot of problem sessions and reviewing. Some of the reactions that we're going to cover you have seen before, like for example, we have seen the dehydration of alcohols into alkenes, and for that you use either sulfuric acid or phosphoric acid. But we're going to actually see new reactions like the oxidation of alcohols, substitution reactions. We're coming back to SN1 and SN2. We're going to see esterification, tosylation, and this one, it's to form ether, so it's a brand new functional group. Now this one over here we have actually just not done, but we're going to see it within this chapter as well. Alright, I have taught you that as soon as you see an alcohol, the first thing that you do is you classify the alcohol. So for example, I have a primary alcohol right here, and for primary alcohols you have 2 different hydrogens attached to your alpha carbon. That's important to actually know because depending on the number of alpha hydrogens, that's how many oxidations you can actually do. So for example, I have 2 alpha hydrogens. If I take one away, if I oxidize once, I get an aldehyde, or I can oxidize again because I still have a hydrogen attached. I can oxidize again to the carboxylic acid. So again, as I actually increase the bonds to oxygen or the number of oxygens, I'm actually oxidizing the reaction, the compound. If you have a secondary alcohol, you only have 1 hydrogen attached to your alpha hydrogen. That means that you can only do 1 oxidation. So you go from a secondary alcohol to a ketone. You cannot do any further oxidation of that ketone, so you stop right here at the ketone. Tertiary alcohols, and you can draw whatever tertiary alcohol you want. But a tertiary alcohol doesn't have any hydrogens attached to the alpha carbon, well, because it's tertiary. So I cannot oxidize a tertiary alcohol. Now, if you're going to do an oxidation of a secondary alcohol, again, the secondary alcohol has only 1 hydrogen attached to the alpha carbon. So you will only be able to oxidize to the ketone. So you will get the ketone all the time. There's not going to be any over-oxidation of the ketone to the carboxylic acid. That's not going to happen. But you can do this reaction with several different reagents. So for example, you can do the reaction with chromium trioxide. You add there sulfuric acid. Or you can do the reaction with sodium or potassium dichromate. I have been telling you that we use sometimes sodium, sometimes we use potassium, but it's just a counter ion, so it's still fine. But when you use chromium, you're going to have to use acid in there. So sulfuric acid is the one that we use most of the time. Now, chromic acid is probably the oxidizing agent, which you will form whenever you actually just make the chromium trioxide or the dichromate with sulfuric acid. Again, classify your alcohol first. So you have a secondary alcohol. There's only 1 hydrogen attached to it, so you can only do 1 oxidation, and that will be your ketone, and you will stop there. If you wanted to actually do it with chromic acid, you can do the reaction that way as well. The mechanism itself is kind of interesting because under acidic conditions, the chromic acid and the alcohol react to form the chromate ester. So there's going to be an elimination of water. I'm going to do what we call a box reaction. This is by no means the mechanism. This is just telling you that we're eliminating water. So the alcohol actually attacks the chromate, the chromium, forming the chromate ester, eliminating the molecule of water. Again, this is all done under acidic conditions. And here's the important part. And here's where that hydrogen that's attached to your alpha carbon comes in. Because what we're going to do is an elimination. We're going to eliminate that hydrogen. For that, you have water in solution. It's important that you have water. The water is going to abstract that proton. We're going to form the double bond of the carbonyl, the double bond between the carbon and the oxygen. And that is going to kick out the chromium. Chromium is going to go ahead and it's going to form this species right here. You have your ketone and your water just picked up a hydrogen, a proton, so it's now a hydronium. If you happen to have a primary alcohol, let me just change the color, things are going to be a little more interesting, more things to do, because now you have two alpha hydrogens. There are two hydrogens on this alpha carbon right here. So what we actually just would do, if you do one oxidation, you would get the aldehyde. There's a hydrogen left, so you can actually over-oxidize the aldehyde into the carboxylic acid. Any of the reagents that I showed you in the previous slide will actually just not give you the aldehyde, which I said that kind of wrong. I'm sorry, I apologize, and I'm gonna just do another error right here. Okay, so the deal is, if you add chromium trioxide or sulfuric acid, or if you add the potassium or sodium dichromate in sulfuric acid as well, one or the other, you will not be able to isolate the aldehyde. What you actually get from this reaction is the carboxylic acid at the end. So these two reagents actually over-oxidize the carboxylic acid. And it has been discovered that it's the presence of water that actually promotes the over-oxidation of the aldehyde into the carboxylic acid. All right, so here's just a little bit of a story. Again, you use two of your favorite chromium reagents to oxidize alcohols, but you discover that when you have a primary alcohol, you're not able to actually stop at the aldehyde state. And then you discover that it's the water present in the solution that actually over-oxidizes the aldehyde into the carboxylic acid. So now what we're going to try to do is that we're going to eliminate water from the chromium reagent. And that has already been done. We're not going to invent anything. Pyridinium chlorochromate is a chromium reagent that it's good to oxidize, but it doesn't have any water whatsoever. So you have your chromium trioxide. You have pyridine. Pyridine is a 6-member ring with a nitrogen taking the place of a carbon. And you actually also have HCl in there. So this is the recipe for PCC. Again, pyridinium chlorochromate, PCC. And PCC is actually excellent into stopping those primary alcohols at the aldehyde state. PCC will not over-oxidize the aldehyde into the carboxylic acid. It can't because it doesn't have any water, and what you need to over-oxidize the aldehyde into the carboxylic acid is water. So PCC, again, will take a primary alcohol into the aldehyde and it will stop right there as an actual excellent reagent to do this reaction. If you happen to have a secondary alcohol, PCC will also oxidize secondary alcohols into ketones, but usually you want the selectivity of going from primary to aldehyde, and that's why you use PCC for this reaction. Now, tertiary alcohols cannot be oxidized because they don't have a hydrogen attached to the alpha carbon. So that's one thing that I need you to do. You need to classify the alcohol and classify it correctly. So if you see that it has a hydrogen attached to the alpha carbon, it can be oxidized with any of the chromium reagents. So again, a secondary alcohol can only be oxidized to a ketone. For that, you can use any of the chromium reagents, the chromium trioxide, the sodium dichromate, or you can even use PCC in a pinch. If you want a primary alcohol to stop at the aldehyde state, only PCC will do that reaction. But if you want your alcohol to be overoxidized to the carboxylic acid, again, you can use any of the other chromium reagents, the chromium trioxide, or the potassium or sodium dichromate will actually do primary to carboxylic acid. There are many other reagents around. For example, the Jones reagent. The Jones reagent is when you just combine the dichromate with sulfuric acid, and then your alcohol, you put it in acetone. So basically, it's the oxidation reaction with acetone as the solvent. The Collins reagent is the chromium oxide in pyridine. You could use potassium permanganate. Potassium permanganate is a strong oxidizing agent, and it will take the primary alcohol all the way up to the carboxylic acid. Swern oxidation, it's a gentler oxidation. I'm going to show it to you in the next slide. But it's a gentle oxidation in which you can take a primary or a secondary alcohol. You use DMSO and you use oxalyl chloride. You do it in the presence of pyridine, and you will take your primary, you'll take your secondary, which is the one that I have here, to the next level up. You could also take a primary. You add DMSO, oxalyl chloride, which I'm going to just write it over here, and pyridine. Or you can write Swern oxidation. And this is important, my little monkeys, because if you have a primary alcohol, Swern will take it to the aldehyde. So it's a second option. Instead of using PCC, you can use the Swern reagent, and you can get that primary into the aldehyde. Now, you have plenty of reactions that you have been learning through the semester. And that's the nature of organic chemistry, is that once you learn the reaction, you have to remember it all the way to the end of organic chemistry. And then you have to learn the new reactions and how can they actually just make a longer synthesis, basically. All right, so we have 1-methylcyclohexene. We're going to do a reaction with borane and hydrogen peroxide. Now, is this reaction Markovnikov or anti-Markovnikov? If you said anti-Markovnikov, you're right. So the OH is going to go to the less substituted carbon. So the OH is going to be over here. Right, I have an alcohol right there. What type of alcohol is this? Is it primary, secondary, or tertiary? It's a secondary alcohol. This alpha carbon is attached to two other carbons. So a secondary alcohol with a chromium reagent, how many hydrogens are attached to the alpha carbon? Only one. Very good. I'm assuming you answered one. So if it's a secondary alcohol, I can only oxidize it once and it will be to a ketone. So this is the product of this sequence of reactions that I have here. I have a longer sequence in the next one. All right, in problem 2, I have 2 different alcohols. The first thing that you always do, as soon as you see that alcohol, I want you to classify them. So this one right here, is it primary, secondary, or tertiary? This one right here is primary. This one right here on the left, is it primary, secondary, or tertiary? Okay, well that one is secondary. When you use the sodium dichromate, the secondary will go to the ketone. What is the primary going to go to in the presence of the dichromate? If you answer the carboxylic acid, you're correct. So I'm going to oxidize that primary alcohol to the carboxylic acid. But notice that my secondary, there's only one thing you can do to a secondary alcohol, and it's oxidize it to the ketone, and that's it. There's nothing else we can do. Now, if you notice down here, I have PCC. This is dichloromethane or methylene chloride. And it's a good solvent for doing the PCC reaction. So you take PCC and the primary will go to what? It will go to the aldehyde. And the secondary will go to the only thing that the secondary can do, which is again the ketone. So notice that the secondary on both, it gave you the ketone. But it's the primary that you actually find a difference right here. So this one is an aldehyde. If you use PCC, and again it's because PCC doesn't have any water, this one is the carboxylic acid. You need to know this because that's part of the fun of organic chemistry. Okay, that's part of my fun whenever I write the exam. I'm going to see if you know how to classify the alcohol, and I'm going to see if you know exactly what the reagents do to the different alcohols. Let's do it longer. All right, this reaction you just learned in chapter 9. So I have a terminal alkyne, and I'm going to add hydrogen in the presence of Lindlar's palladium. Do you remember that reaction? What type of alcohol did it give you? First of all, I'm sorry, it didn't give you an alcohol. It reduced the triple bond to the double bond. 1, 2, 3, 4, 5. I have 5 carbons. It reduced the triple bond to the double bond. This is a syn addition of hydrogens. But you have a terminal double bond, so you won't be able to actually see the syn addition. All right, now I have a terminal double bond, and I'm adding water in a little bit of sulfuric acid. This one right here, Markovnikov or anti-Markovnikov? Ah, very good. This is the Markovnikov one. That means that your alcohol will go on the more substituted carbon. So it's going to be now a secondary alcohol, which when you actually oxidize with chromium trioxide and sulfuric acid, will get you a ketone. So we have gone from alkyne to alkene to alcohol to ketone. Let's go back to the alkene because we did a Markovnikov addition here. This is borane. This is the anti-Markovnikov. So now you get the less substituted alcohol. So the OH would be on carbon 1. This is a primary alcohol now. And you have to be careful because in the presence of chromium trioxide or the dichromate, the primary alcohol will go to what? Do you remember? The carboxylic acid. I know I didn't put it in here, but let's add PCC so that we can see the difference. Primary in the presence of PCC will get you the aldehyde. All right, this concludes the first part of chapter 11. I'll be back with the second part of chapter 11. I wanted to go back to the end of the chapter and see if you can do 5 or 6 problems on the material, the reactions covered in this section. Bye.